Section 9.1, Example 2 on page 688, we have sometimes you can see the pattern in a sequence by comparing each term to the one that came before it. For example, in the sequence 133, 130, 127, 124, each term after the first term is equal to 3 less than the previous term. A recursive definition for this sequence contains two parts. Part A, an initial condition, the value of the first term, a sub 1 equals 133, and B, a recursive formula, relates each term after the first term to the one before it. For example, a sub n equals a sub n minus 1 minus 3 for n greater than 1. Example 2 says the number of blocks in a two-dimensional pyramid is a sequence that follows a recursive formula. What is a recursive definition for the sequence? The first step to finding the recursive definition is to figure out the terms in the sequence. So for our first block, we have 1. Next, we have a pyramid of 3. Then we have 6, 10, 15, and 21. So this gives us the terms of our sequence. Now we can take the second term and subtract the first term. We get 3 minus 1 equals 2. If we take the third term and subtract the second term, we get 6 minus 3 equals 3, and so on. 10 minus 6 is 4, 15 minus 10 is 5, 21 minus 15 is 6. So we have the general form down here, a sub n minus a sub n minus 1 will give us n. Notice here we had a sub 6, this ended in 6, a sub 5, 5, a sub 4, 4, and so on. For our recursive definition, we need a sub n by itself. So if we add a sub n minus 1 to both sides, we get a sub n is equal to a sub n minus 1 plus n. And now we have our two parts. The first part is the initial term, which was 1. The second part is the recursive formula, a sub n equals a sub n minus 1 plus n. The work for this problem is written out on the next few slides. And now I would like you to try number 3. Write a recursive definition for each sequence. 100, 10, 1, 0.1, 0.01.